Welcome. I'm thrilled to be opening the new advanced track at WebCamp Zagreb. I've been hoping for this for a long time, for a place for slightly more advanced talks than like for the regular public. So I'm happy to be the first speaker here. Works better when you turn it on. So just for anyone who doesn't know me, my name is Luka Kladaric. I am the Chaos Manager at Sakura Collective. We are a consultancy that deals with chaos. We don't do greenfield development. We won't do features on your website. We won't put buttons on your website. We won't build your mobile app. But if you are drowning in tech debt, if you have performance or security issues, we'll put you on the right track and then hand off to an in-house or external team that'll take you the rest of the way. So this is my 5th talk at WebCamp Zagreb since 2012, but also it's the first one in 2 consecutive years. I've always taken a gap year. So before we get into the actual talk, what do I mean by the platform in the title of my talk? So I'll be talking about internal hosting platform, so the shared environment that all engineering teams use to host any kind of backend application, web or otherwise. So I'm going to quickly look back at 2017. 2 years ago, I gave, feedback. 2 years ago, I gave a talk called Zero Downtime Data Center Failovers, Switching Hosting Providers for Dummies. I gave this talk at a couple of conferences and meetups in this neighborhood. It was basically about how we executed a zero downtime migration to a completely different cloud provider, and the tech stack that let us do that. So today I'd like to update on that, but the contents of that talk isn't that necessary to understand this one. So I'm going to give you an update on the deployment and pain. I'm going to give you an update on that deployment and the pain that we noticed over time and what we replaced it with. So just to quickly get you up to speed, the old stack that we were using was Ansible, Jenkins, HA Proxy, Nginx, and Isinga. So Ansible was our config as code tech of choice. We declaratively described how we wanted our servers to be configured, which software needed to be installed, and so on, but also we abused it for actual deploys, for getting new versions of code out to servers. Jenkins was our CI/CD tool of choice, so building artifacts and then shipping them out with configurations using Ansible. We used a dedicated repository, Git repository, to house all of the Jenkins jobs. Of course, all of it is declarative config as code, so we can inherit configurations between jobs. So we just have a master Android build job and a master Python build job, and then you inherit from that and just override with the specifics of an application. So we have maximum code reuse. It was great. I loved it. I didn't come up with it, but I contributed it to a lot, and I loved it. It's great if you're familiar, but if you're just trying to jump in and find the thing, like find a job for your application and tweak it slightly, it's impossibly complex. HA Proxy was our load balancing service and software. It was auto configured from Ansible. It's very powerful, very flexible. But if I'm being honest, we weren't really using that much of the advanced features. Nginx, we needed this. This is just an added complexity that we didn't have to need, but we did end up needing it because we would put multiple Python applications on a single box. So Nginx was on that box and routing requests to the actual application that was requested, which meant that we had to configure, if we wanted to add a new virtual host to one of our application, we would have to add it to both HA Proxy and to Nginx. And the Nginx was in each box, and the HA Proxy was distributed. So it was just one more thing to keep track of, and was mostly in the way. I don't remember a single time when it actually gave us something. Isinga was our primary internal monitoring solution, also auto-configured from Ansible, mostly out of the way, did its job with very little complaining. And it was good. The platform was good. It did the job. It allowed us to pull off a very complex data center / provider failover without losing any requests. So during the week or so that we were moving application per application, even if you somehow ended up in the wrong data center with your request, it would still get serviced. It might not be the fastest request you've ever seen from us, but it would get serviced. The platform allowed us to build an exact replica of our entire environment over at AWS. It let us grow. We added applications to it, mostly without any trouble. There was some manual work from the ops team, but for the most part, we added, we grew by 50% the number of applications that we host. It's not a lot, but it worked. It let us scale out. We also added capacity by scaling horizontally and vertically easy. easily. You could add another box, or you could grow the existing boxes. It was simple to add more machines and provision them quickly to do the same type of work. And we didn't need more. It was a small team of engineers, about a dozen. We trucked along happily without significant hiccups for about a year. And that was when it was the first time when I went, we don't really support that. And what was the request? The request was Python 3. Now that shouldn't be difficult, but it was. We made it happen though. A colleague figured out a way for an app to run Python 2 or Python 3 on the same actual box with just a few lines of configuration changed. And then someone asked for Golang, and we were just stumped. Our entire pipeline was Python or Java, and Java was just completely different from Python. So to do Golang, we would have to do a third completely different deployment pipeline, build and deploy pipeline. And we had built so many solutions like you define the app, but also you define how the health checks work, and it works in Python and Java, and we would have to figure out all of that stuff again for Golang. And then the next day someone would ask for for the fourth thing. And this was roughly the first time that I heard Kubernetes suggested as a solution, or just requested because everyone else was using it. But I truly liked what we had. I didn't want to throw it out, certainly not for something like Kubernetes, which would require throwing everything out and replacing it with basically similar components. So we had no expertise with Kubernetes and no experience, even if I'm being honest. So the platform served us really well. We went from 100 requests per second when we did the migration. So I don't even know what the rate of request was when we first built it. It was roughly when I first joined the company. So, but it was 100 requests per second when we migrated to AWS. Last I checked, it was 2,000 requests per second. So that's a 20x increase, but it never goes below 400 a second now. So that's a 4x increase from maximum to like minimum, and a 20x increase maximum to maximum over 2 years. And we didn't have to do anything. Sometimes the HA proxies, the load balancers would run out of bandwidth, increase their size, but the thing didn't break in ways where you go, oh, we're going to have to redo the entire thing. Traffic scales, you scale, but so it worked. It served us really well. So what actually broke? What made us start looking for a replacement? It wasn't the Python 3. It wasn't the Golang. It was the background workers. It was a perfectly reasonable request from the engineers of an existing Python application, and we didn't have anything like it already. And we spent way too much time building support for it. It broke all of our assumptions about the platform starting at day one. Like the first things that we assumed were wrong, and it ended up being this monstrosity. And a year later, I still hate going into that pipeline, that part of the Ansible codebase. To have to do anything. So it became apparent that we reached the end of the road with this platform. So why? It was because each thing had its own deploy pipeline. It's because each thing, the complexities of each different application, each different type, but also each individual application, stretched all the way to the end of the pipeline. So when a thing is weird in a different way, you have to have a weird different pipeline all the way through. So what's the answer to this problem? It's containers very, very clearly. Containers let you concentrate complexity handling in the build stage, close to where the complexity originates, the source code. So once you have an image, the deploy is exactly the same, regardless of the stack. You could be shipping Java, Python, Go, Rust, whatever you want, side by side, because it's all contained in the container. That's why it's called containers. But also, when we started looking into this, we wanted to make it possible for teams to self-manage most, if not all, of the infrastructure for their applications. We wanted to make sure that if they had an idea, they were able to at least spin up a dev instance of it without bothering ops. Because we didn't want to be bottlenecked. We didn't want to be the bottleneck for the entire engineering organization. So, how do I containers? I spent a few days trying to cram containers into our Ansible HA proxy Jenkins setup. And the more I looked at it, the more miserable I became, and the more components I threw out and replaced with more natural fits. So what did we replace? Jenkins was the first thing to fall and be replaced with Travis. Jenkins is self-hosted, so that means that it's either bored or over-provisioned or another thing you manage scaling for. Travis is a much better fit for a high-velocity engineering team because they handle the scaling. So when you're not asking it to do anything, it's not doing anything. And when you're asking it to do many things, it scales out and does many things. Travis file is also a lot easier to understand than a Jenkins file, just for the syntax. And building container images allows the teams to explain the complexities of their code base locally and to fully control how their applications are built and deployed. So, okay, using Travis, we built a container image. What now? How do you run a container on the internet today? There's Kubernetes that I already mentioned, a couple other bad attempts at solving the problem, then a whole lot of nothing, and then Amazon's ECS. Oh, there's also something called Fargate. So, ECS, Elastic Container Service. I like to present it as Kubernetes, but built with AWS primitives. So the services that we know and love that we've been using for years, like Elastic Load Balancer, Route 53 for DNS, and so on. So ELB is used to route requests to your containers. Route 53, the DNS service, is used for service discovery. It's all of the things that we use for other normal projects, legacy projects. They're just used slightly in a different way. Fargate is, I've read a bunch of documentation on it. I haven't found a single good explanation for it, so I came up with my own. Apologies if I stole someone's, but it's serverless ECS. It's Elastic Container Service that lets you run containers, but without having to explicitly declare, here's how many workers I have, and here's how big they are. Here's how many machines I have. So you just say, I want to run containers. Here's an image. Give me 10 instances of it, and you get 10 instances of it. You have no idea where they're running. Slightly scary, but it's also awesome because it's one less thing that I have to worry about. And if Amazon falls over, that's just way above what we're capable of doing better ourselves. So you get to forget about where it's going to run, about cluster capacity. You get to spin up 10x and spin down in the middle of the night, and you don't have to care. I'm not an expert on Kubernetes. From what I know, it makes it easy to start building a massively distributed system and very painful to maintain it in production. I dislike the kitchen sink approach. And from what I've heard from people who actually do it on a massive scale, you do need the human resources to run a data center before you consider Kubernetes for production use. I may be 100% wrong. I welcome anyone to come and talk to me about it after the talk and convince me otherwise. So far, I haven't been successfully convinced. So ECS, Fargate, right? I like the concept a lot, and I just ran with it. Initial expeditions were painful. The console supporting both classic vanilla ECS and Fargate is very confusing. You have to click through a bunch of things, and once you're done, you have no idea what you clicked in the start to get it to run. So it's completely, you cannot successfully iterate using the console. So what do? You go to CloudFormation. CloudFormation is infrastructure as code, so it's not a one-to-one mapping for Ansible, but we don't want to do manual configuration management anymore, so it's what we consider the replacement. It's declarative creation of Amazon resources. You say, I have an application. I need this application to be connected to a load balancer. I need this application to have a database. I need it to have a cache. I need it to have an access to an S3 bucket, and so on and so on. This CloudFormation also lets us deploy the basic shared stack for all of our Amazon accounts. So VPCs, subnets, gateways, firewall rules, load balancers, DNS zones are all in one template. So when we decide we need another zone, so we have a production zone, a test zone, a dev zone, and so on. If we need a fourth, I just create a fourth account and say, roll out that template to there. And everyone knows that they can expect the same network setup, the same layout, the same basic utilities in there. And the application CloudFormation templates know that they can call on that and expect it to be there. So that means that an application CloudFormation template only describes what that application needs. Simple reuse means app templates are short and only contain the resources necessary for their operation. CloudFormation console is awesome because you get to see who deployed what. You get to see when things changed. And if something doesn't need to exist, you delete the CloudFormation stack from the console, and it deletes all of the resources that were provisioned for it, all of the databases, all of the buckets, all of the everything. So Icinga got replaced with CloudWatch. Not much to say here, really. It's inferior in terms of configurability, frequency, resolution, but it wins on the grounds that it's one less thing that I have to worry about. It just works and doesn't need to be hosted. So it's one less thing that goes down because we mess something up. HA proxies, like I said, we weren't really using any of the advanced features, and we were already running all of the requests through a central load balancer to distribute between our redundant HA proxies. So we just threw HA proxy out of the mix, and we just use ELB directly. By this point, some of you are like, yes, I know all of these things, but how did you actually implement it? So the base networking CloudFormation stack, like I said, contains the VPC, the private network, the subnets in that network, the private and the public subnets, the ones that are accessible from the outside, the ones that aren't, the internet gateways, and so on. It also contains a DNS zone, so each account has its own zone. So we have dev.company.com, and prod.company.com, and internal.company.com. So every app just says, I need app name dot, and it gets app name dot dev dot something. You don't have to, deploying an application, you don't have to say you're going to be the dev application, so you have to behave like dev, just inherits all of the resources. The load balancers, both private and public, we can have applications that are only accessible from the internal network or from the public network. The ECS cluster, where we deploy the containers, the security groups, who can access what, and so on. It's all deployed from GitHub via Travis to all AWS accounts on each commit. We also have the ability to roll out just a dev for trying out things, but that's what it is. So when I need to add, recently I had to add something for databases to be able to work, for serverless, whatever, added it to the template, it's rolled out to everything. And the CloudFormation template, the stack for an individual application, it defines the task definition, the service. Those are ECS things that define how many instances of a container you need, how many is considered healthy, how many, and so on. What the size of those containers should be in terms of CPU and RAM. It defines a target group, which is just like the place where containers register to start serving traffic. The listener rule, which defines which host name the application responds to. The log group, so automatically all containers log to the same place. Task role and policies. This is very cool. Each application gets its own task role, and you can attach policies for what it's allowed to do within Amazon directly there. So if I need an application to be able to read from a bucket, I can just put it straight in the policy, and that's it. And also the DNS entries, any additional DNS entries, and so on. So everything is in one repo. The actual application code, Python, Java, Go, whatever. The Docker file that explains how that application is built. The CloudFormation template that explains how that thing is deployed, and the Travis file that actually explains how all of those link together. Which branches are built, which branches are deployed, which branches are tested. It's easy to follow, even if you're seeing the repo for the first time. So you ask, where's application foo? You go there and you see everything. The CI/CD flow is, you push to the repo, Travis builds the image, sends it to ECR, that's Elastic Container Registry. And then the next job is the deploy, which runs the CloudFormation. CloudFormation tells Amazon, here's all of the things that I need for this application to do, to run, and CloudFormation on Amazon's side goes, okay, these are the differences, so here's what we're gonna do. The cool thing is that different branches are different environments, so you can have a dev branch and a test branch and a prod branch. So what are the actual end user benefits? And by end user, I mean developer. All context and complexity about an application is in a single repo. Introducing weird applications and things to the ecosystem doesn't make things weird for others. You have your own weird thing, we have our own weird thing, they don't mix. There's no self-managed single point of failure. Sure, there's single points of failure in Travis and in Amazon. Travis isn't mission critical to run, it's mission critical to deploy. And at Amazon, when it goes down, that's not a problem that we've attempted to solve yet. It's trivial to add new environments. Like I said, we have 3 or 4. We need a 5th for some reason. Here you go. We could easily use this to roll out an environment in a different continent. The really, really cool thing, and this is the one that I get all of the developers with, is see pull requests live before you merge. So as soon as a pull request is made, because we've described all of the things that an application needs to be launched, we can spin up a temporary version of it. Application name -pr26.dev.company name. And you can see it, you can try it. If you did visual changes, you can see the visual changes live. If you have a QA team that clicks through an application before it goes live, they can do that with your instance. It's trivial to autoscale. I'm using trivial a lot here because it truly is. You say, I need this application to run 5 instances, and if the CPU load on them is 80%, then spin up 5 more, and spin down, and so on. So the hurdles that we saw with this, CloudFormation is extremely fragile starting out. It's a slightly hostile environment. It takes a lot of trial and error to get to a place where you're being somewhat productive. The first deploy of a new CloudFormation template, if it fails, you cannot retry it. You have to go in and delete the failed one. Otherwise, usually when you try to do a change and it fails, it just goes back to the stable state. But there's no stable state for this, so it just hangs in limbo. It's annoying. ELB rule priority is a weird one where, for historic reasons, elastic load balancer rules have to have a numeric priority which is unique, and it makes absolutely no sense for routing requests based on virtual hosts. So www goes to this app, and account dot goes to a different app. It doesn't matter which one is resolved first, but for some reason you have to assign numbers. It's a big problem to come up with unique, stable numbers for things in a distributed system. But the biggest hurdle was building the legacy applications in Docker. I cannot explain how frustrating it is to take things that have been building in the Wild West and try to cram them into the nice restrictions of Docker. But this would happen with any tech. So even if you're not ready to pull the trigger on something like this, start building your applications with Docker, just even for local use. You'll thank me when you start going into something like this. And that's it. Questions?
Thank you, Luka. We do have time for one question. Maybe 2 if Luka is particularly good. So, here.
Yeah.
What about serverless tech?
Lambdas and stuff, yes, completely out of the scope of this talk. This is for proper backend applications. Serverless has its place in time. That's not what I'm talking about here. So I'm happy to talk to you about it outside, but that's not what this talk is about. Sorry.
Certainly one more question then.
So I guess your developers don't write the CloudFormation YAMLs?
Not initially, but the intention is that the infrastructure team provides templates. And actually, yes, we have developers that write CloudFormation for, not for this specific thing, but for like databases, Redshift, and so on. The intention is that the entire engineering team ramps up on CloudFormation and is able to self-service to a certain point, but the ops team is going to retain expertise in it.
And what about local environments? Do they nowadays use mostly AWS stuff when they are even testing locally, if they are testing something more complex?
That depends on the complexity of the application. If it is possible to have a local instance, I always advise that you have a local instance. It's always faster to iterate that way. But some things are just way too complex, and some things you just have to test in the cloud. We're done?